Here we'll be looking at different number bases. So we'll begin with an introduction to explain what that's all about in case you don't know anything about number bases at all. The Vedic methods are independent of the number base used, so we'll be seeing how they apply in different number bases. But first we'll see how to convert a number to base 10. Base 10 is the number we normally use. So given a number in a different base than base 10, how do you convert it to base 10? Then we'll be doing the reverse of that, which is converting a base 10 number into a number in another base. Then we'll look at addition and subtraction in different bases, multiplication near a base, something on converting decimals, converting to and from base 10 when the numbers are less than a whole one. Then we'll just briefly refer to some other applications in divisibility testing and in trigonometry. So first of all, let's look at base 5. Base 5 is our kind of guinea pig because once you understand the principles in base 5, you'll see how to apply in other bases. So let's just look closely first of all at base 10. These are the 10 digits that we use in base 10, the digits from 0 to 9. And after 9, of course, we have 10, 11, 12. In another base, in say base 5, it's different. Whereas in base 10 we have 10 symbols from 0 to 9, in base 5 we have 5 symbols from 0 to 4. So in base 6 we'd have 6 symbols from 0 to 5. And we don't use the other numbers. In base 5 we just use these 5 digits. And just as in base 10, if we want to go beyond 9, we have 10, 11, 12, and so on. And we go on through all the 2-digit numbers up to 99, and then 100, we go into a 3-digit number for the first time, and so on. In base 5, once we get to 4, we go to 10. Because we can only use the digits 0, 1, 2, 3, 4 in different combinations, and we can't use any number beyond 4. So after 4 comes 10, and that's equivalent to the number 5, because we know that after 4 comes the number 5 in base 10. So this 10 here is a base 5 10, but it's equivalent to 5. After 10 comes 11, in which we have a 1 unit and a 5. Okay, this one here stands for 5, this one here stands for 5 in ordinary base 10 terminology. This one stands for 5, so this is 6. 5 and 1 is 6. And then 12 will be 7 in base 10. And then we would say 13, and then 14. What comes after 14? Actually, it's not 15 because we're not allowed a 5, so now we go on to 20. And we go on like that. After 20, we'd have 21, 22, 23, 24, and after 24, we go to 30. And we go on like that through all the 2-digit numbers in base 5 until we get to 44. 44 is the biggest 2-digit number we can have in base 5, because the 4 is equivalent to a 9 in base 10. 4 is the biggest digit you can have in base 5. So after 44, what do we have? 100. And then 101, 102, and so on. So that's how it works in base 5. If you find this a little puzzling, you might want to just listen to this introduction again up to here. So what we might need to do is to convert a number in base 5 into our ordinary base 10 numbers. And if a number's in another base, we put a little number like this. Here we've got a base 5 number. This is the number 32 in base 5. So the little 5 just indicates what the base is, base 5. What's this number in ordinary base 10 numbers? Well, we know that a unit in this position is worth 5. And we've got 3 units there, so that's 15, and 2 more makes 17. This is the number 17 in base 10. We can just leave it as 17 and understand that if there's no subscript, then it's a base 10, or you can write base 10. It doesn't really matter. So we convert a 2-figure number in base 5 into base 10 by multiplying the left-hand figure by 5 and adding on the units figure. So if we had 42 in base 5, 5 times 4 is 20, and 2 is 22 in base 10. What about a three-figure number, 213? Well, if you just think for a moment about a base 10 number, 213, if it was 213, this would be 2 hundreds, 1 10, and 3 units. In base 5, though, these are the 1s, 5s, and 25s. The third figure from the right is the 25s column, which is similar to our ordinary base 10 system, in which the value of each column goes up by 10. So we have the 1s, 10s, hundreds. So this column was 10 times bigger than the one before, just as this column is 10 times bigger than the one before. So if this column here is 5 times bigger than the one before, then this column will be 5 times bigger than the one before that. So a unit here is worth 5 times a unit here, and the unit here is worth 5 times a unit here. So this is the 1s, 5s, 25s, and if we were to go on, it will be 5 times 25, 125 in the fourth column. So how can we convert this base 5 number into base 10? We use just the same technique, which is a bit like the osculation technique that we've been using for divisibility testing. And the idea is to multiply the left-hand figure by the base number and add on the next number. So we multiply 5 times 2, which is 10, add on 1 to get 11. And then 11 times 5 is 55, and add on 3 to get 58. So this is the number 58 in base 10. So if you had 3, 2, 1, for example, in base 5, you'd multiply the 5 by the 3 and add on the 2, and then you'd multiply the result of that by 5 and add on the 1. So 5 times 3 is 15, and 2 is 17. 17 times 5 is 85, and 1 is 86. Let's try a four-figure number. 1, 2, 3, 4 in base 5. Let's convert that to base 10. Use the same technique. We're going to multiply the 1 by 5 and add on the 2. Multiply the result by 5 and add on the 3. Multiply the result of that by 5 and add on the 4. And that's the answer. So 5 times 1 is 5 and 2 is 7. 7 times 5 is 35 and 3 is 38. 38 times 5 is 190 and 4 is 194. Okay, just the same pattern can be used in another base. Let's look at base 6. There's the base 10 numbers. And in base 6, we've got 6 digits, 0, 1, 2, 3, 4, 5, and we have no digits beyond 5. So again, after 5 would come 10, 11, 12, 13, 14, and then we're allowed 15, but we're not allowed 16. After 15 will come 20. And then 21, 22, and so on, up to 25, and then 30. So suppose we want to convert 32 in base 6 into base 10. We use exactly the same technique as before, but we multiply by 6 and then add on the next digit. So it's 3 times 6, add on 2. 3 6s are 18 and 2 is 20, so that's the base 10 equivalent of 32. 213 in base 6, we do the same thing. 6 times 2 is 12 and 1 is 13. 13 times 6 is 78 and 3 is 81. And for a four-figure number, 6 times 1 is 6 and 2 is 8. 8 times 6 is 48 and 3 is 51. 51 times 6 is 306 and 4 is 310. So those are the base 10 equivalents of those base 6 numbers. Let's look at base 3. Here we only have 3 digits, 0, 1 and 2. So after 2 will come, well, 10. And here the 1 here is equivalent to a 3. So this is equivalent to 3, and of course the number after 2 we know is 3. After 10 will come 11, and then 12, and then not 13 because we can't have a 3 here, it'll have to be 20. Then 21, 22, we can't have 23, so after 22 comes 30, and so on. So what about 21 in base 3? We use the same technique. 3 times 2 is 6, and 1 is 7. It's 7 in base 10. And you can see that here. In fact, these are roughly lined up. This is 3, this is 4, this is 5, this is 6, and the next one will be 7. 21 is equivalent to 7. So that's 2 3s and a 1 is 7. 1 2 1 base 3, we do the same thing. 3 times 1 is 3, and 2 is 5. 5 times 3 is 15, and 1 is 16. That's the number 16 in base 10. And a 4-figure number, 3 times 2 is 6, and 0 is 6. 6 times 3 is 18, and 1 is 19. 19 times 3 is 57, and 2 is 59. Here's a 5-figure number. Same thing, we multiply this 1 by 3, we get 3. Add on 0 is 3. 3 times 3 is 9, and 1 is 10. 3 times 10 is 30, and 2 is 32. 3 times 32 is 96, and 2 is 98. So the columns here are worth 1s, these are 3s, 9s, 27s, 81s. They go up in powers of 3. Finally, let's have a look at base 2, which is quite an important base because it's used in computing. We just use 0 and 1 in computing language, where 1 can be a pulse of electricity and 0 can be no pulse. So we only allowed the digits 0 and 1 here, so how do we count with just 2 digits? Well, after 1 we'll have to have our 10. Because we can't go on to 2, we'd have to come to 10 then. And 1 more than 10 is 11, which is permitted. And 11 is number 3. You can see that because in base 2 the columns will be worth 1s and 2s. So this one here is worth a 2, and with that added on it gives you the 3 that we had in base 10. That's the number 3. What's the number 4? Well, we can't go on to 12 because we're not allowed a 2 here. So what comes after 11? Well, 11 is actually equivalent to 99 in base 10 because 1 is the biggest digit you can have. And after 99 comes 100, so that's what we're going to have here. We have to move into the next column, and 100 is the number 4. And if you think about it, the columns will be worth 1s, 2s, 4s, so that one is a 4. So this is actually equivalent to 4. And then you'll have 101, 110, 111, and then it'll be 1,000. That'll be 8. 1, 2, 4, 8. That one's worth an 8. This is the number 7, and so on. So let's convert 11 in base 2. Well, we already know that. We've already done that here. It's the number 3. But if we apply our method, we say 2 times 1 is 2, and 1 is 3. For 110 in base 2, we do the same thing. We multiply the 1 by 2, we get 2, and 1 is 3. 3 times 2 is 6, and 0 is 6. This is the number 6. There it is. 1, 2, 3, 4, 5, 6. Here's a 5-figure number. Same thing, we multiply 1 by 2 and add on the next number. So 1 times 2 is 2 and 0 is 2. 2 times 2 is 4 and 1's 5. 5 times 2 is 10 and 1's 11. 11 times 2 is 22 and 1 is 23. This is the number 23. And if you wanted to check it, you could say, right, that's the 1's column, 2's, 4's, 8's, 16's. So we've got that one is worth 16, that one's worth 4, 2, and 1. And that comes to 23 if you add up 16, 4, 2, and 1. Okay, you might like to practice this exercise now in changing these numbers in other bases into base 10. So if you'd like to pause and try these. So here are the answers if you'd like to check. You see the number 94 has got 3 representations because 94 in base 10 is just 94. There's the number in base 6 and there's the same number in base 3. So we can represent a number in different bases. And this can have advantages. For example, here we've just got ones and a 0, so it'd be quite easy to manipulate that number, maybe easier than using the number 94. So that's how we convert numbers in various bases to base 10. What about the alternative process, converting a base 10 number into another base? So first of all, we're going to look at converting to base 5. Suppose you want to convert the number 47, which is a base 10 number, into a base 5 number. What's the equivalent base 5 number? Well, whereas in converting the other way, we kept multiplying by the base number 5, here we're going to divide by 5. So we divide 47 by 5, and we get 9, remainder 2. Now that 9 is a base 10 9, because the division was done in base 10. The remainder, because it's going to be less than 5, can be base 10 or base 5. So we can consider that 2 as part of the answer. It's a base 5 number. What we've got to do now is to convert the 9 into a base 5 number. And so we divide 9 by 5. 5 into 9 goes once, remainder 4. And then the 2 goes on the end. And the 1 there being less than 5 can be just left as the answer. 142 is the answer in base 5. So we said 5 into 47 is 9 remainder 2. 5 into 9 is 1 remainder 4, and put the 2 on the end. And because we've ended up with a 1, which is permitted in either base, we get 142 base 5 as the answer. What we're doing here is finding out how many we can put in each of the positions. This is the 1s, 5s, and 25s, remember. 1s, 5s, 25s. So if we want to know how many 5s there are going to be, we simply divide this by 5 and we get 9 remainder 2. But because 9 is not permitted, we have to convert 9 into a base 5 number, which is 1 remainder 4. And that tells us that there's 1 lot of 25 and 4 lots of 5 and 2 units. Let's take the number 74 and do the same thing. We'll convert this to base 5. We begin by dividing 5 into 74. Well, that's 14, remainder 4. Now, although the digits in 14 are both below 5, that 14 is actually a base 10 14, because when we did the division by 5 here, we did it in base 10. We got 14, which is an ordinary base 10 14, remainder 4. The remainder, of course, can be base 5 or base 10 because it's below 5. So we need to apply the same thing now to the 14 and divide 14 by 5. How many 5s in 14? 2, remainder 4, and there's the last 4 on the end. And so we get 244. One more example, 321, convert to base 5. How many 5s in 321? Well, 6 5s are 30, so there's 2 left over. 21 divided by 5 is 4, with 1 left over. So now we divide 5 into 64. 5 12s are 60, so it's going to be 12, remainder 4, and then the 1 on the end. Now 5 into 12 is 2, remainder 2. 2, remainder 2, and then 4, and then 1. 2, 2, 4, 1. Let's look at some other bases now apart from base 5. Let's convert 47 to base 7. So as you probably realize, we're just going to be dividing by 7. How many 7s in 47? 6. That's 42, so we've got 5. Now that 6 is actually going to give us the answer because 6 is permitted in base 7, so the answer is 65 in base 7. Convert 84 to base 6. We divide 6 into 84. Well, 6 into 8 is 1, remainder 2. 6 into 24 is 4, remainder 0. Well, we've got a 14 here, so we can divide by 6 again. 6 into 14 is 2, remainder 2, so we get 2, 2, 0 in base 6. Convert 1, 2, 3, 4 to base 4. We're dividing by 4. 4 into 1, 2, 3 is 30, remainder 3. Now we divide 4 into 30, we get 7, remainder 2. 3 goes on the end. The 7 needs to be dealt with as well, and that's outside the limit of 4, so we're going to divide 4 into 7, which is 1, remainder 3. So 1, 3, 2, 3, base 4. And 23 into binary. Binary is base 2, so I'm going to be dividing by 2. 2 into 23, that's 11, remainder 1. Now the 11 has to be divided by 2, which is 5, remainder 1. That's the remainder 1, and that's the 1 from here. Now 2 into 5, it goes 2, remainder 1. Put the other ones on. Finally, 2 into 2 is 1, remainder 0, and I can put those down. 1, 0, 1, 1, 1, base 2. Okay, why don't you try these? Pause and try these. Well, these are the answers. Now let's look at addition in base 5. We can put our addition totals for the basic digits in a box like this, in a table like this. The only digits in base 5, of course, are 0, 1, 2, 3, 4, and we've got those along the top, 0, 1, 2, 3, 4, and down the left-hand side, 0, 1, 2, 3, 4. And in each box, we put the total of the number above and to the left. So 0 and 0 is 0. 0 and 1 is 1. 2, 3, 0 and 4 is 4. Here we put 1 and 0, the total of that 1 and that 0, which is 1. 1 and 1 is 2, 3, 4. Here we've got to put the total of 1 and 4. 1 and 4 is 5 in base 10, but we don't have a 5 in base 5, so we have to put 10 here. Okay, the next number after 4 is 10 in base 5. It's equivalent to the number 5. Next row, 2 and 0 is 2. 2 and 1 is 3, 4. Again, we have 2 and 3, which is 5, so that's a 10. And then 2 and 4 is 6, which is 11. Okay, this is a 5 here and a 1 here, which is 5 and 1 is 6. So of course we can work this all out, and we can use our converting method if we're not sure. So for example, 4 and 4 is 8. We can make 8 into a base 5 number by dividing by 5. 5 into 8 is 1, remainder 3. So we get 13. Anyway, we end up with this table here. This is the full table for the additions. And we can use this for our adding. Suppose you want to add 32 and 41, where these are base 5 numbers, and of course the answer is going to be in base 5. Well, let's do this from right to left. 2 and 1 is 3, and that's fine. That's true in base 10 or base 5. Here we have 3 and 4 is 7 in base 10, we either convert 7 into base 5, or we use our table for adding that 3 and 4. So if I want to add 3 and 4, it'll be this number here. 3 and 4 is 12. So I can put that 12 down. Let's take another example. 324 and 241. Again from right to left. 4 and 1, well, let's see. 4 and 1 is 10. Put down 0, carry 1. Now in the next column we've got 2 and 4. We add up 2 and 4. 2 and 4 is 11. And with the one we carried we get 12. Put down 2, carry 1. In the third column we have 3 and 2. 3 and 2 is 10. 10 and the carried 1 is 11. Put those down, we get 1120. Let's do that same addition from left to right. 324 and 241. So 3 and 2 are added first of all, and 3 and 2 comes to 10. Put down 1, carry 0. In the next column we have 2 and 4. 2 and 4 is 11. Nothing to add on, so it's just 11. We put down 1, carry 1. In the last column we have 4 and 1. 4 and 1 is 10. But you remember when we add from left to right, the carry is 10 times bigger, so that's really a 10. And so that as 10 is added on to the 10 from here, giving us 20. 2, 0. Let's just take one more example. Let's have 324 and 332 from left to right. So 3 and 3 is 11. Put down 1, carry 1. 2 and 3 is 10. 10 and 10 is 20. Put down 2, carry 0. Finally, 4 and 2 is 11. Nothing to add on, so we just put 11 down. 1, 2, 1, 1. Well, you might like to try this. You can do them from left to right or right to left or both. So these are the answers. And other bases we can handle in a very similar way. Now let's look at subtraction in base 5 first of all. And we'll look at a special case to begin with, subtracting from a base number. So here we see 1000 take away 241. If it was an ordinary base 10 subtraction, and these were base 10 numbers, then we could do this easily by taking each figure in 241 from 9 and the last one from 10. So we get 759. The sutra changes if you've got a base of 5 because 9 is equivalent to 4. 4 is the largest digit you can have in base 5. And so the sutra, all from 9 and the last from 10, becomes all from 4 and the last from 10, where 10 is actually 5 in base 10. So if we apply that sutra now to this subtraction, then we'll be taking this 2 and this 4 from 4 and this 1 from 5. So 2 from 4 is 2, 4 from 4 is 0, and 1 from 5 is 4. We get 204, and if we were to add these numbers 241 and 204 in base 5, we will get 1000 in base 5. Here's another example, 100,000 take away 30241. So again, we've got 5 figures here and 5 zeros here. We can take each digit here from 4 and the last one from 5. So we get 1, 0 from 4 is 4, 2, 0, 4. We take the 1 here from 5, we get 4. Here we've got 4 zeros and 3 digits. So we need to think of this as being 0333. in order to have the same number of figures here as the number of zeros here. So 0333, applying the sutra, we take the 0 from 4, which is 4, the 3 from 4, which is 1, 3 from 4, which is 1, and 3 from 5, which is 2. As mentioned before, the techniques we've learned for base 10 also apply in other number bases in Vedic maths. Now let's just look at some other bases. Suppose we had this subtraction in base 3. The same principle applies because we're subtracting from a base number. So here the sutra is going to say all from 2, because 2 is the largest digit in base 3, all from 2 and the last from 3. So we take each of these from 2 and the last one from 3. 1 from 2, 2 from 2, and 1 from 3 is 2. Here's a base 7 subtraction, and we've got 4 zeros here and only 3 figures, so we need to insert our 0 in front, or imagine it. And the sutra now says all from 6 and the last from 7. So that 0 gets taken from 6, leaving 6, then 3 from 6, 6 from 6, and 3 from 7. 6304. One last example, here's a base 2 subtraction, but again we've got a base number here. Let's see, we've got 5 figures there and 5 figures here, so we can simply apply the sutra, which is going to be all from 1 and the last from 2. All from 1 and the last from 2. So 1 from 1, 1 from 1, 0 from 1, 1 from 1, and 1 from 2. The answer is just 101 in base 2. So that's a special kind of subtraction where we're subtracting from a base number, and it can be extended, but we're going to go on to general subtraction. So suppose we want to subtract in base 5 and we want 43 minus 21. That's very easy, of course, because we can simply take the 2 from the 4 and the 1 from the 3. That's true in base 5 and in base 10. For 42 minus 23, if we do the same thing, we'll have 4 take away 2 is 2, and 2 take away 3 is bar 1. So we get 2 bar 1, and we want to convert that into positive digits. Well, this 2, of course, means 20. It's 2 5s, and we've got to take 1 off of that. So we need to think about the number that's 1 less than 20, which will be 1 4. Because if we add 1 to 1 4, we get 20. The next number after 14 in base 5 is 20. We did have another way of subtracting. Let's just look at that. Suppose we had 42 minus 23 again. The other way was to start at the left, do the subtraction, and check if we need another unit in the next column. So here we would say 4 take away 2 is 2, but we'd only put down 1 and put the other one up here because we can't take 3 from 2. And now we would have 12 take away 3 to do. Well, you can either convert that into base 10 subtraction, it'll be 7 take away 3 is 4. Or you can look at the table, 12 take away 3, here's 12, take away 3 is 4. So we get 14 again. Now in this 3-figure subtraction, we can do it the bar number method. 3 take away 1 is 2. 2 take away 4 is bar 2. And 3 take away 4 is bar 1. So we've just got to clear those bar digits. And this is like taking 21 from 200. It is taking 21 from 200. So we're going to have a 1. That 2 is going to become a 1. And then we can apply the sutra, all from 4 and the last from 5 to the 21, to get the other figures. We did something just like this in base 10. So we take 2 from 4 to get 2, and 1 from 5 to get 4, and there's the answer, 124. The other methods, 323, 144, 3 take away 1 is 2, but we put down 1 because we need 1 up here because we can't take 4 from 2. We now have 12 take away 4. 12 take away 4 is 3, but we don't put down 3, we put down 1 less, which is 2, and put the other one up here because we can't take 4 from 3. 13 take away 4. 13 take away 4 is 4, and so we get 124 as we did before, the other way. So you might like to try this exercise. It's the addition table on the right to help you if you'd like to pause and try this. You can use either or both of the methods that I've shown on the previous slide. Now let's look at multiplication in base 5. Again, we can fill out a multiplication table like this. So in this box here, we will put the product of 0 and 0. 0 times 0 is 0. 0 times 1 is 0. So these are going to all be zeros. And down here too, we'll get zeros because 1 multiplied by 0, any number multiplied by 0 is 0. 1 times 1 is 1, 1 times 2 is 2, 1 times 3, 1 times 4. 2 times 1, 2 times 2, 2 times 3 is 6, and we're not permitted 6 in base 5, so it's going to be 11. And 6 is 1 and 1. That's a 5, that's a 1. And then we have 2 4s are 8, and 8 is 13. Or we can just add 2. Obviously, these are going up in 2s. 0, 2, 4, 6, 8 in base 10. And we can fill the whole table in like that. And we end up with this table here. So suppose you want to find 32 times 3 in base 5. We can use the table to work it out. The usual way, of course, is to start at the right and say 3 times 2. 3 times 2, according to the table, is 11. So we put down 1 and carry 1. 3 times 3, well, that's 14 in the table. 14, and we want to add 1 on. Well, if you add 1 on to 14 in base 5, you're going to get 20. So we get 201. Let's do 213 times 2 the same way. 2 times 3 is 11. Put down 1, carry 1. 2 times 1 is 2, and 1 is 3. 2 times 2 is 4, which is permitted, so we get 431. 1, 2, 3, 4 times 4. So we start with 4 times 4, which is 31. Put down 1, carry 3. 4 times 3, 4 times 3 is 22, and we've got to add 3 onto that. Well, you can use your addition chart from before. You can just add on 3 units, one at a time. After 22, you'll get 23, then 24, then 30. So 22 and 3 is 30. Put down 0, carry 3. Now we have 4 times 2, and 4 times 2 is 13. I've got to add 3, to carry 3, onto the 13. So if I add them on in ones, I'll get 14, 20, 21. I get 21, put down 1, carry 2. Finally, I have 4 times 1 is 4, and 2 is 11. 11101. So that's straightforward short multiplication in base 5. You might like to try these for practice. So here are the answers if you'd like to pause and check. And now let's move on. We're still going to be working in base 5, but we're looking at vertical and crosswise multiplication. And we'll be looking at multiplying two two-figure numbers together. So suppose we want 32 times 13. I'll just write them out. I'll do these right to left. We begin by multiplying 2 by 3, and 2 times 3 is 11. Put down 1, carry 1. Now we have the crosswise step. So we have 3 times 3, which is 14. 2 times 1 is 2, and we have to add 2 to 14, which gives us 21. And with the carry, we get 22. Finally, we have the vertical on the left. 3 times 1 is 3, and 2 is 10. 1021. Let's take another example. 23 times 43. We begin with 3 times 3, which is 14. Put down 4, carry 1. Crosswise, we have 2 times 3, which is 11. I'm going to write this on one side. 2 times 3 is 11, and 3 times 4 is 22. So I've got to add those up, which is obviously 33, and I've got 1 to add on, the carry, which is 34. Put down 4, carry 3. Now vertically on the left, I have 2 times 4, which is 13, and I've got to add 3 onto that, so I get 21. So 2144. 34 times 24. I begin with 4 times 4 on the right, which is 31. Put down 1, carry 3. Crosswise, I get 3 times 4, which is 22. To write it over here, 22. 3 times 4, and now 4 times 2, which is 13. So I need to add those up, and I can use my addition table on the right there if I want to. But I can see that's going to be 3 in the tens column and 1 coming over from here because that's a 10. So I get 40. 40 and the carry 3 is 43. Put down 3, carry 4. Then finally I've got 3 times 2, which is 11, and 4 is 20. 2031. So the vertically and crosswise multiplication technique works in this base, and in fact it works in any base. We'll take one last example, multiplying two three-figure numbers together, 421 and 323. And beginning on the right, we have 1 times 3, which is just 3. Then we'll have the crosswise step here. 3 times 2, that's 11. And 2 to add on is 13. Put down 3, carry 1. The next step is to multiply the 4 by the 3, the 2 by the 2, and the 1 by the 3. So I'm going to write the steps out to make it absolutely clear. So 4 times 3 we know is 22. 2 times 2 is 4. And then 1 times 3 is 3. Well, I can take the 22 with the 3 because they complement each other. 2 and 3 is 10, so that's going to make 30. 22 and 3 makes 30, and with the 4 that's 34. And with the 1, the number after 34 is going to be 40, so I put down 0, carry 4. The next step is this cross product here, 4 times 2 and 2 times 3. So I'm going to have 4 times 2, which is 13. Let's write it. And 2 times 3, which is 11. That gives me 24. So I've got to add the carry 4 on to 24. To add 24 and 4. Well, if you look at the table here, you see 4 and 4 is 13. So I'm going to get a 3 and a 3 with the carry. I get 33. So put down 3 and carry 3. And the last step is the 4 times the 3. 4 times 3 is 22. And I've got to add on 3, which gives me 30. So there's the answer, 303033. Well, you might like to practice these. Why don't you try these 4 multiplications? If you pause here and use vertically and crosswise to multiply these numbers in base 5. So these are the answers that you should have got, hopefully. And now we're going to move on. Multiplication near a base in base 5. Can we use our method for multiplying numbers near bases in other bases? Well, we can, and we're going to illustrate that in base 5. An example of multiplying two numbers in base 5 that are nearer to a power of 10 would be 34 times 43. Remember that the largest digit in base 5 is a 4. So 43 would be very close to the base of 100 in base 5. It's only 2 away. And 34 also, we've got large digits. These are the two largest digits in base 5, 3 and 4. So let's see if we can apply our technique. So let's see, we have 34 times 43, and the method is to write the deficiency from the base next to the number. How much is 34 below the base of 100? Well, we can apply our formula, of course, all from 4 and the last from 5. That's probably the easiest way of doing it. So we'll take 3 from 4, and the last one we take from 5. This is 11 below the base. If we apply the same rule here, we take this from 4 and this from 5, and we just get 2. This is only 2 below the base. Now you remember the technique, we cross subtract. 34 take away 2, that's 32. And we multiply vertically, 11 times 2 is 22. And there's the answer. We can also cross subtract the other way as well. 43 take away 11 is also 32. 3222. Take another example, 44 times 44. These are clearly just below the base. So 44 times 44 are both 1 below the base. I'm going to put 0, 1 for the first one at least, because we know that the base there is 100, which has 2 zeros. Now I'm going to cross subtract. 44 take away 1, that's 43. And multiplying vertically, I get 1 times 1 is 1, but I need to put 0, 1. And so we get 4301. One more example. Here's a couple of 3-figure numbers. 442 and 431. To get the deficiencies, we take these from 4 and the last from 5, so we just get 3. I'm going to put 003. Here I get 0, 1, 4. Now cross subtracting, I can go either way. I think it'll be easier to take 3 from 431. I can just take the 3 off. So taking 1 off 431, that's 430, and then 1 below 30 is 24, and so I'll have 423 here. You can do a separate subtraction for that if you're not sure. 423 is what it comes to. And now we've got to multiply 3 times 14. So 3 times 4 is 22. Put down 2 and carry 2. 3 times 1 is 3, and 2 is 10. I am allowed to put both those figures down because I've got 3 figures on the right hand side. So there's the answer, 423, 102. Well, you can practice some of these. Here's an exercise. Can you multiply these using a base method? And here are the answers if you'd like to check them. Now let's look at converting base 10 numbers which are decimals into other bases. So for example, if we had the base 10 number 0.7, we may want to convert it to base 2. Now, of course, in base 10, 0.7 means that the position after the decimal point is the tenths, and then hundredths, thousandths, and so on. In another base, it will be different. So in base 2, for example, the position after the decimal point will be halves, and then quarters, eighths, and so on. And in base 3, the position after the decimal point would be thirds, and after that would be ninths, 27ths, and so on. So let's see about converting 0.7 into base 2. We're going to be continually multiplying by 2 like this. So we multiply the 7 by the base number 2, we get 1.4. 0.7 times 2 is 1.4. 1.4. Now we multiply the 0.4 by 2, we get 0.8. 0.8. We multiply the 0.8 by 2, we get 1.6. 1.6. We multiply the 0.6 by 2, we get 1.2. 1.2. We multiply the 0.2 by 2, we get 0.4. 0.4. We multiply 0.4 by 2, we get 0.8. And you'll see we're starting to recur because we've had 0.8 before here. And so from here it starts to recur. In fact, from here to here, it will recur. So we have 0.1 and then the block of 0, 1, 1, 0 will keep repeating. So that is the base 2 equivalent of 0.7, base 2. Now let's convert 0.7 into base 3. So this time we're going to be multiplying by 3, but doing just the same thing. We multiply 0.7 by 3, we get 2.1. We multiply 0.1 by 3, we get 0.3. We multiply 0.3 by 3, we get 0.9. We multiply 0.9 by 3, we get 2.7. We multiply 0.7 by 3, we get 2.1. And of course it's starting to recur here. Once we get that 0.7, which is this 0.7 here, it'll start to recur. So from here to here, it will recur. So that's the base 3 equivalent of 0.7. Let's convert 0.4 to base 7. So we're going to multiply by 7 at each step, and 7 times 0.4 is 2.8. 7 times 0.8 is 5.6. 7 times 0.6 is 4.2. 7 times 0.2 is 1.4. And there we've come to the 0.4 that we started with, and so this is going to recur. So those four figures, 2, 5, 4, 1, will recur over and over. So that's the base 7 equivalent of 0.4. Convert 0.23 to base 2. We're going to be multiplying 23 by 2. So 0.23 times 2 is 0.46. 0.46 times 2 is 0.92. 0.92 times 2 is 1.84. 0.84 times 2 is 1.68. 0.68 times 2 is 1.36. 0.36 times 2 is 0.72. 0.72 times 2 is 1.44. And we go on like this. If you'd like to pause and carry on, there are 22 figures after the decimal point before it starts to recur, so it goes on for quite a while. I'll put up the rest of these now. So here are the next few figures, and you can see it starts to recur. We've got 1.84 here, which we had at this point, 1.84, and we had 0.92 before it, which is here. So in fact it recurs from here to here. There are 20 figures in that recurring block, and the halfway point comes here. And you may recall in our recurring decimals that sometimes we had complements from 9 between the first and second half of the recurring decimal block. And something similar is happening here, because if you look at the numbers after this division, we have 0, 0, 0, 1, and here we have 1, 1, 1, 0. These are complements from 1. Each pair adds up to 1. In fact, you can see a similar thing happening in the others as well. If you split this one in half, we have 2, 5, 4, 1, and the 2 and the 4 make a 6, and the 5 and the 1 make a 6, which is 6, of course, is equivalent to 9 in base 7. Here we'd expect the complements to add up to 2, and we have, here's the middle point, we have 2 and 0 is 2, 0 and 2 is 2. And the same here, if we split here, we get the 0 and 1, the 0 and the 1 there make 1, and the 1 and the 0 make a 1. So if we knew when we were halfway, we could get the second half from the first half. If you look at this example here, we've got a remainder of 0.6 there, and you can see that 0.6 and 0.4 make a 1, a whole one, and that's the halfway point. Similarly, if we look here, when we've got 0.3, it's the complement of 0.7 from 1, so that was the halfway point. The other ones are slightly different because there's a non-recurring number before we get the recurring block. Here you'll see that the 0.6 that occurs just before we get the second half starting is the complement of 0.4. 0.6 and 0.4 add up to 1, and that's the number just before it starts to recur. So if we knew it was going to recur from there, we'd be looking out for 0.6 for our halfway point. And the same here. We've got 0.92 here before it starts to recur, and so we're looking out for 0.08, and when that comes up, we're halfway through, and we can take the first 10 digits away from 1 to get the second 10 digits. Well, let's move on. We're going to look now finally at the converse process of converting decimals which are not base 10 into base 10. So here, for example, we've got 0.1011, and it's a base 2 number. So this column is the halves, this is the quarters, this is the eighths, this is the sixteenths, and so on. What is the equivalent of this in base 10? I'm going to write that number out with more space. That's our base 2 number. Previously, to convert the other way, we were multiplying by the base number 2 from left to right. Here we're going to be dividing by the base number. So we start at the right here, and we divide 1 by 2, which is 0.5, and add on the next number to get 1.5. So we're going to continuously divide by the base number and add on the number in the next column to the left. So the next step is to divide 1.5 by 2 and add on 0. 1.5 divided by 2, that's 0.75, and adding on 0 is 0.75. Now 0.75 divided by 2 is 0.375, and I'm adding on the 1, so I've got 1.375. And finally, I divide 1.375 by 2 and add on 0. I get 0.6875. And that's the answer. That's the base 10 equivalent of 0.1011 in base 2. Let's take another example. 0.231 in base 4. So here we're going to be dividing by 4 and adding on the next digit to the left. So 1 divided by 4 is 0.25. Add on 3 is 3.25. Divide 3.25 by 4 and add on 2. That's 0.8125, so that'll be 2.8125. Now divide 2.8125 by 4 and add on 0. We're going to get 0.703125. And that's the answer. Now we can convert 0.34, a base 5 number, into base 10. So 0.34 in base 5, I'll be dividing by 5. So 4 divided by 5 and then add on the 3. 4 divided by 5 is 0.8, so I get 3.8. 3.8 divided by 5 is 0.76, so I get 0.76. That's the answer. Convert 0.8 in base 9 into base 10. 0.8. It's a base 9 number, so I'm dividing 8 by 9, which is 0.8 recurring. So that's the answer. There are other applications of the Vedic methods in number bases. For example, in recurring decimals, we can use the same techniques for converting fractions like 1/19 in base 10. The methods that we use there are equivalent methods in other bases as well. The methods still work in other bases. And among applications and uses of number bases, we could mention divisibility testing and trigonometry. For example, this is the well-known expansion for cos x. When x is in radians, we get this power series. We see that each term has an extra x squared in the numerator and that the signs alternate. And so cos x can be written as a number 1, 1 over 2 factorial, 1 over 4 factorial, 1 over 6 factorial, and so on, in base minus 1 over x squared. So we can actually work out sines and cosines by converting the number in this base, minus 1 over x squared, into base 10, and the reverse. And similarly with other functions, sine x, e to the x, and so on. So that's the end of this lesson. We, of course, had the introduction into what number bases are all about and how to convert a number in another base into base 10, and the other way, converting from base 10 into another base. We saw how to add and subtract using the Vedic methods. We saw that they still applied in different bases and that we could use our special cases as well. General multiplication and special multiplication also apply. And then we looked at converting decimals to and from base 10 and those other applications.